So let's review for the Unit 8 exam, Chapter 25 and 26. These are the topics I'm going to go through. We're going to talk about the definition of electric potential, and we'll talk about potential in a uniform electric field, E field. Then we'll talk about the potential of point charges, and then from that we'll briefly discuss continuous charge distributions, although there is nothing like that on the test. Then we'll talk about voltage around charged conductors and what you need to know for that. Then that's basically Chapter 25. Chapter 26, we'll define capacitance. We'll talk about parallel plate capacitors, combinations of capacitors in series and parallel, energy stored in a capacitor, and dielectrics. And pretty much all these topics, except for the continuous thing, will be covered on the exam. So let us begin. So electric potential, again, it's one of those, so electric potential, and as I said before, there's lots of ways of saying electric potential. They say electric potential, they say potential difference, they say change in voltage or just voltage. It all means the same stuff. How much work did you have to put into a system to get a charge located somewhere in an electric field? That's the way you deal with it in electrostatics. See, if I've got some kind of electric field, okay, here's some E field, and I want to move a charged particle through that field, let's say from point A to point B. Now, some outside agent has to do work to move this thing through that electric field, right? Because what do electric fields do? They apply forces to charged particles. That's the definition of electric field. They apply forces to charged particles. So this E field is applying a force to this guy. So if I'm going to move it against the field, I've got to put energy into this system. So I am increasing the voltage as I go from A to B. And here's the way we defined a change in voltage. And really what we're dealing with is changes in voltage from one place to another. Okay? And the change in voltage is, well, we're going to, if I do work against the field, that is, the displacement is, overall against the direction of the field is doing negative work. I'm putting positive work into it, but really the displacement is in the opposite direction. So if I gain voltage, if I go E dot ds, or ds is a displacement vector, and it's negative, okay? Because look, if I just look at the E dot ds, what is that? Electric field times the displacement, right? And what does the dot mean? How parallel they are, right? You only do work when the component of the electric field is parallel to the displacement, or vice versa, whatever. So here, here's a little tiny ds. Look at that little ds right there. It's so cute and infinitesimal. So there's my ds, and notice that it's against the electric field. So if I just went E dot ds, that would be a negative quantity, but I'm putting work into this. I'm gaining voltage, so to make that negative thing a positive, you multiply by negative. So this is the definition of a change in voltage. Now let's think about that in terms of potential energy. We had a very similar definition for what a change in potential energy was equal to negative F dot ds. I don't know if you remember that or not, but we did it. And all we're doing really is dividing it by the charge on my test charge. We'll call it Q naught. Q naught. And this right here is my definition for voltage. And what is the force divided by the charge on the object that has force, that has the force on it, that's the electric field, right? Okay. And we said this is a joule per coulomb. We called a joule per coulomb a volt. Make sure you remember that a volt is a joule of energy or a joule of work done per coulomb of charge that you're moving through this field. Okay. Now, using this definition for voltage right here, well, it's pretty easy. If the E field is uniform, right? If you have a uniform field like this, so then, okay, so here E is a constant field. This becomes pretty easy because delta V equals negative, integral E dot ds. But the electric field is a constant. And what happens in integration when it's a constant? It comes out of the integral, negative E, dotted with the sum of all the ds's. Well, what is the sum of all the ds's? The sum of all the little displacements. And you can use, sometimes we use ds, sometimes we use dr. I'm sorry, it's whatever people happen to be using. That is that's your total displacement. So the change in voltage is equal to negative E dotted with delta S. And again, I can't remember if in the book we used, no, we used ds in the book. And then, of course, the displacement vector is sometimes called dr. Now, look. This is a dot product. So I'm probably going to give you a problem on the test where you move an object with charge on it, say it's positive charge, you move it like this, from here up to here somehow. So what do you not care about? You don't care about the vertical displacement. You only care about the amount of displacement that is parallel to the electric field. That's one way to look at it. Or if I give you this in IJ form, you can evaluate the dot product with unit vectors. Make sure you know how to do that. You remember I dot I is 1, J dot J is 1. What is I dot J? Zippo. Okay, so there will be a problem on the test where you simply have to know this. And you have to know that that it's a dot product. The biggest mistake students will make is they'll forget about the dot product and they'll just multiply the magnitude of the electric field times the magnitude of the displacement. I mean, they'll actually do they'll figure this out using Pythagorean theorem or something like that, and it's the wrong answer. And you lose a lot of points for that. If you make that mistake, if you don't treat it as a dot product, you're going to lose probably 5 out of 10 points. Okay? So make sure you remember dot product. Okay, so we've defined electric potential. We've talked about it in a uniform field. Let's talk about point charges. And here's basically what we did. If we have a point charge or a collection of charges that has spherical symmetry, right? It acts like it's a point charge if you're outside of it. Okay, and here's this electric field. Do we know what this electric field is? Yes, we do. We said that E is equal to KQ over R squared in the R hat direction, right? If it's positive charge, it's away. If it's a negative charge here, that negative is assigned to the R hat, meaning the field lines are going towards the charge if it was negative charge. And so then we applied delta V to this, and this was negative KQ over R squared. And then we went ahead and said dr. I mean, we did say ds, and we took the dot product, and the dot product means we only care about the radial component of the displacement. And we did all this. Now, then we went from our initial to our final, and we evaluated this integral. I'm not going to redo the whole derivation. You can go back and look at the video or read the book for that derivation. But basically what we did is we said, where is our initial position? Where are we deciding to make the potential energy 0? And we said for this, a point charge, we said infinitely far away. Because when you evaluate this integral, the negatives will go away, and you basically get a v equals kq over r, and we just say that r initial is infinitely far away. Well, when you divide by infinity, you get 0. That's why the potential is 0 at infinity. We push a charged particle from infinity all the way to some location r from that. And so that's the final voltage minus the initial voltage. Well, the initial voltage was 0. And so we get this expression. This is the voltage around a point charge. What does this mean? If I have a point charge right here, or I mean a test charge, I had to do work against this field to get it here. This is how much work I did per unit of charge on my test charge. Now, if it asks how much potential energy is stored in this, well, then you would go, well, remember that energy, U, is equal to Q times the voltage V. But this Q is the Q of my test charge right here, Q naught, or whatever you want whatever charge is right here. Okay. What if there were 2 point charges? And I want to know where the voltage is. Maybe there's another point charge over here. Doesn't have to be positive. I like to be positive. All right. Well, this has an electric field. And, almost crossing field lines, don't mean to do that. So that if I add a positive charge here, these field lines will change. Okay. But I can't do that with a pencil. So, but what am I going to do? I have to do work now to get to this location in space against the field of this charge and the field of this charge. And the nice thing is we just add them together. So how much potential is right there? V equals K, Q1, we'll call this Q1, over R1, that is the distance from my test charge to Q1, plus K, Q2 over R2. We just add them together. It's very simple. And look at how nice this is. These are scalar quantities. Voltage is a scalar quantity. So I don't have to mess around with I hat, J hat, or any of that craziness. I just add them together as scalars. That's why physicists love dealing with voltage rather than electric field. Because voltage is easier to work with. Then you just take the gradient of this to get the electric field. Anybody can do that. All right. Now, and if I put multiple test charges around it, well, you just keep adding them up. Dot, 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 plus K. If I have N charges, you just keep adding and adding and adding. Of course, we have a way of saying this. V equals the summation of I equals 1 to N of K Qi over Ri. Right? Of course, the K comes out, but I'm just going to leave it like that. Now, if I have, instead of a whole bunch of point charges, if I have a continuous charge distribution, well, you just change these discrete charges, K, or Q1, Q2, and so on, to infinitesimal charges, and you sum them all up. The summation sign becomes an integral sign. And you go K dq over R. And of course, the K comes out of the integral. dq has to be in some way put in terms of R or some distance, like sometimes we use X or something like that. I don't think there's a, I'll do the problem rundown, but I just did it for some people, and there's no integral problem on the test. You will get one on the AP test, though, so it's worth studying. I mean, we'll have to know it eventually. No, you are. Oh, you're taking like a whole bunch of AP tests.
Well, yeah, I'm not taking the.
If you're not taking the AP test, but you're taking lots of AP tests. So, and one of them is your final exam, so you will have to know how to do that. Yeah. Oh, I didn't tell you that. All right. Oh shoot, the drop date hasn't gone by yet. All right. Okay, so now we're going to talk about the voltage around conductors. Now, let's suppose we have a conducting sphere. And by the way, I think this was I don't think we watched this video in class. I think I told you to watch it at home because we ran out of time. So if you haven't watched the video on the voltage around conducting spheres, make sure you watch it. But I'll try to repeat. Suppose we got a sphere. It doesn't have to be a sphere, but we'll make it a sphere. All right. And this is a conductor. So where is all the charge on it? It's all on the outside. None of it's interior. Because you can't have an electric field within the interior of a conductor. So this is all on the outside. Now I want you to think very carefully here. From out here, what does the electric field look like of this charged metal sphere? It looks like a point charge. The electric field is indistinguishable from that of a point charge. So I can say, well, V out here, this is for a conductor, V out here is just KQ over R. All right, now let's suppose this has a radius of R. So what is the voltage? This is the voltage, V equals KQ over R, when R is greater than or equal to the radius. Okay? Does that make sense? All right? I mean, when you're at the surface, your voltage at the surface, I mean, how much work did it take to push a point charge there? Well, I'm working against this field of a point charge all the way to get to that surface, so it's just going to be KQ over capital R. I mean, if little r equals capital R, you're on the surface, and that's how much work you did. But what is V equal to when R is less than the radius of the sphere? When your distance away from the center is less than the radius of the sphere. Like right in here. You see you're right there. Okay, quite often the guess is 0. And that's a good guess. It's wrong, but it's a good guess. There is something that is 0 inside that sphere. The electric field is 0. But what is voltage? Voltage is a measure of how much work it took for me to get that charge there from infinity, from infinitely far away. So here's what I'm doing. Yeah, I'm doing all this work, I get to the surface. I'm inside now. I'm inside the sphere. I don't have to do any more work. But what happened to all that work it took me to get there? It's still there. I mean, it's still part of the system. I mean, what if I drift out of this sphere? What's it going to do to my test charge? Ping! It's going to shoot it off. So their potential energy is still there. Here's a really beautiful analogy of this. Think of this as inside the sphere is kind of like the top of a mesa. And here, this is a parabolic slope here on the mesa. And the height here represents how much work. So if you have a bicycle, okay, here you are riding a bicycle. Your hair's in the wind. All right. And you're riding your bicycle, and you're really, really far away. So the slope is very, very gentle. And it doesn't take much work to ride your bike, right? But then you start climbing, getting closer to the top of the mesa, and it gets steeper and steeper, and that's because the electric field is getting stronger and stronger, but I have to do more and more work, and it's getting harder, and I'm doing more, and I'm really putting a lot of work into this, but then I get in here, and it's like, but I still have height above where I started. I still have the energy I put into it per unit charge. So that's voltage. So think of this. The electric field out here is very steep. Very, very strong field as you get closer. Here, what's the slope of this? 0 slope, 0 electric field, but all that energy is still there inside. So inside that conductor, we would say the voltage is KQ over R. everywhere inside. Oh, this should be we. Should have well said we, but when r is less than. So when you're inside the sphere, it's just or whatever. Now this was for a something that had spherical symmetry, but this works no matter what the charge symmetry was. That if I have a conducting surface, and here this represents this is the conducting material inside here. So it's got charge here on the surface, cross section. And, of course, the field lines, they come off perpendicular. Always, field lines always come off perpendicular to, no, this is assuming an electrostatic condition. So I have to do work against this to get all the way to this surface. But once I get inside, the voltage is a constant. The voltage is a constant inside a conductor. Let me show you something really cool about why this is true. Remember we said that a change in voltage is equal to negative E dot ds, right? Well, let's take away the integral sign. Well, if I take away the integral sign, this delta V becomes a dV. Shit, that's a V right there, not a U. dV equals negative E dot ds. Now, here's what I'm going to do. I'm going to make this all in the x direction because I really don't want to deal with partial derivatives and gradients yet. And then I change this and I say, well, E is equal to negative dV dx. Well, what is this? If I look up here, this is a slope, right? So there's dV dx. So the higher I go, the more the steeper the slope, right? And the greater the electric field as I get close to this sphere. Oh, I'm sorry, I'm off screen there a little bit. But so that's kind of cool. And the slope is in the opposite direction. Okay, but here's something else that's very cool. What do we know the electric field is like inside a conductor? We said the electric field inside a conductor is 0, right? Well, the derivative of what is equal to 0? A constant. The voltage inside a conductor is constant. Okay? Because the E field is 0, V equals a constant inside a conductor. So all this calculus theory makes sense, but it also makes intuitive sense if you think like a positive test charge, okay? You go, oh, working against this field, working against this field. Oh, I don't have to work against nothing anymore. But all that energy I put into it is still there. So the voltage is a constant, not 0. The electric field is 0, but the voltage is a constant. And you can kind of see when you look at the calculus of it. All right, where am I? There's some other things. This is really not on the test, though, but if you have a teardrop shape or something with a point on it, let's say you have a round shape like this, I don't know, an ice cream cone on its side, or somebody with a party hat over an ear. The charge is this. If you have an electrostatic condition on a metal, let's say this is a conductor, it's all on the surface, but this is an equipotential surface. What does equipotential mean? The potential is equal, everywhere the same. There can be no potential difference between point A and point B on a conductor if it's electrostatic. Because if there was a potential difference between A and B, you would have a current flowing between the potentials. Current would flow. You would have an electric field along the, if there was a potential difference between A and B, that means along the surface you would have to have an electric field parallel to the surface. That electric field would drive charges to move. So by saying it's an electrostatic condition, you're saying that means that between any point on the surface of this conductor, the voltage is constant. Now, but the charge density doesn't have to be, and it can be shown that closer to a point, the at the point, the charges get very crowded on that surface, but then they spread out, and they're on a rounded surface, they're much more spread out. And why is that? Well, because going from infinity to the surface, you have to do the same amount of work if you're a test charge. You've got to work against the field, work against the field, work against the field. Well, here, these field lines spread out very quickly because they're at a point. Whereas here, the field lines are more parallel. So you have to do work against field lines to get from here over to here. They're fairly uniform, so you don't need a very high field close to the surface, so you don't need a real high charge density near that surface. But if here the point, they're spread out, so here the field is quite weak, but you got to do the same amount of work, so that field has to get quite strong close to the point. A strong field means you have a high charge density there. It's crowded charges. Okay. Really beyond the scope of what I put on the test, but good stuff to know anyway, because the universe is just interesting. All right. Now we get to chapter 26, capacitors. What is capacitance? Capacitance is basically we have a metal of some kind with a charge on it, and we say the capacitance of that arrangement is the charge we put on that metal divided by the potential difference between that positive charge and wherever the negative charge is. Okay, this is capacitance. Coulombs per volt. A coulomb per volt is a farad. Now, it turns out that you don't need very much charge. Well, we deal with very, very tiny charges, amounts of charge. In a capacitor, usually these are millionths of a coulomb, even trillionths of a coulomb. And that's why we usually deal, F is for farad, but usually deal with microfarad. So what does that micro mean? Times 10 to the negative 6. What if it's a picofarad? 10 to the negative 12. A millionth of a millionth. They do nanofarads sometimes, I think. Billionths. All right. Now, here's a cool thing. A capacitance will always be, will always have a mathematical structure where you end up with something that is just the essential geometry of the arrangement times constants of nature. And we did this with a sphere. Super easy to derive. Let's say I got a sphere with charge on it. Okay, on the surface it's a charged sphere. We always deal with metals. It's a charged sphere. Oh, where's the negative charge? Oh, it's everywhere, spread out in the universe somewhere. And we know, so what is capacitance of this? Well, it's the charge on it, Q, over the voltage. Well, that's KQ over R. Well, we'll call it this capital R. And so the charge cancels, and we get C is equal to the radius over the electric constant. That's exactly what we said. First, the capacitance of a charged sphere. There's only one thing that's essential about the geometry of a sphere, and that is its radius. Time the constants of nature. Sometimes this is called, or written as 4 pi epsilon naught times R, because 1 over K is 4 pi epsilon naught. That's how they write it in the book, but R over K is perfectly good. Now we have parallel plate capacitors. That's the most common kind. And we did a derivation of this. I'm not going to repeat that derivation, but if I have two plates that are parallel to each other, connected by a wire of some kind, and some battery or something puts a bunch of positive charge over here, negative charge over here, get an electric field between those plates. Okay, and well, the capacitance of this is the charge on one of the plates. And what is the essential geometry of a parallel plate capacitor? Well, it's got a certain area, and so area A, and it's got a distance between the plates D. That's it. Those are the only things you can change. And we went through a bunch of derivations, but we said that the capacitance is equal to epsilon naught. Oh, there's epsilon naught again. Times the area over the distance between the plates. Now look at the capacitance of a parallel plate capacitor, and look how similar it is to the capacitance of a charged sphere. I didn't really talk about this in the original lecture, but look, epsilon naught times the essential geometry, area over distance between the plates, and here's just radius. But notice dimensionally. What is dimensionally? What is area? It's meters squared. What's D? That's meters. So this is meters times whatever units epsilon naught has, well, farads per meter, and then well, look at R. Same. So dimensionally, it's the same, and that's good. So you had problems dealing with capacitors like that. Then we came up with some symbols. Well, we need some way of putting charge on here, and what we do is we hook it up to a battery of cells. Oops, okay, that's not there. Okay, and battery just boosts the voltage up and puts it in there, and so we've got this now. The parallel plate capacitors are so common that we really use a cross section of a parallel plate capacitor as the symbol for a capacitor. It just looks like this, right? Now you might think, oh, what about? No, these are not the same. Okay, as this, and so that's what you got. Now, when we had capacitors in parallel and in series, this is the first time we've dealt with things that are in capacitors, in parallel. Did I do that right? Yeah, I think so. All right. So that means if they're in parallel, that means, okay, here's my battery. And all this stuff is at a high voltage. And then we got to jump across the capacitor here, or we could jump across the capacitor here to get back down to 0 volts. So things that are in parallel have the same voltage. And look, if I got certain amount of charge here, and then I look, maybe this is a much bigger capacitor. We'll make it bigger. Okay. Well, this one holds more charge, right, for the same voltage. It's a great bigger capacitor. Okay, but how much total charge are we storing? Well, we're just all this. So we're just adding charge for the same voltage drop. Things that are in parallel have the same voltage drop. Like this 12-volt battery, you're up at 12 volts here, you're at 0 volt here. Jump down. And we are jumping down in voltage because look, the electric field inside that capacitor is like this. So when voltage man walks around the circuit and he's holding his little test charge, jumps across with the electric field, that means you're losing voltage. When you move with the electric field, you're losing voltage. And that's what you're doing there. Okay. So we said that these capacitors just add. So capacitors in parallel, they just add. So the equivalent capacitance, in other words, what one capacitor could I replace those two with, is just C1 plus C2, whatever these are. Like this is 3 microfarads, maybe this is 4 microfarads, so this would be a total of 7 microfarads. You just add them together, easy. And it makes sense. It's not just easy, it makes sense. Okay, yes it does. Maybe you don't make sense, but I don't know. All right, who does make sense? None of this makes any sense. Why are we here? Now, in a here are 3 crazy capacitors. They all have different capacitances, different distances between the plates and areas and stuff like that. Maybe you even have dielectrics in them. That dielectrics is the material between the plates that multiplies, increases the capacitance of the capacitor. But C1, C2, C3. What is the same? Well, if this pumps a certain positive charge here, these positive charges cannot jump across the plates. If you have charge jumping across the plates of capacitor, you have a burned up magic smoke capacitor. And we don't want that. We are going to pretend like that's not going to happen. It's not going to happen on the test. So then you would have, well, an equal amount of negative charge here, but that has to come from somewhere because these were all electrically neutral. And so that means that there's positive over here. Negative here. Ooh, positive here. Negative here. So each capacitor has the same amount of charge on it. But when I look at it in terms of voltage, okay, I jump up in voltage across the battery, but to get to zero, I have to jump down, jump down. It takes 3 jumps to get back down to zero. Therefore, these capacitors are sharing the voltage. That is, the voltage of capacitor 1 plus the voltage of capacitor 2 plus the voltage drop across capacitor 3 is going to be equal to the total voltage delivered by our battery. Does that make sense? Okay. Are you phoning a friend over there? No. Okay. So, now, I'm not going to go through all the math of this again, but the fact that Q1 equals Q2 equals Q3, the charge is all the same. And by the way, look, I think I did this in the original lecture, but look, if I just eliminate these and just don't even look at them, whoop, oh, look, 4 charges up there, negative 4 down here. So the total charge of the equivalent capacitor is the same as the charge on each individual capacitor when they're in series. Hey, it makes sense. Now, you combine these ideas plus the definition of capacitance equals Q over V, and here's what you get. The equivalent capacitance here is 1 over C1 plus 1 over C2 plus 1 over C3, etc. So you'll need to know this, and you'll need to know this. And, of course, I'll give you a capacitor that's in combination. Oh, is that too fast? Here. I'll just slow down to 0.5 speed for you. Sukdeep. You're immortalized. All right. Okay, so now, of course, what I'm going to do is I'm going to give you some crazy circuit. Here's a capacitor. Here's another capacitor. Oh, there's one right there. Oh, there's another one right there. And then there's another one right here. And here's A, and here's B. And I'll say, okay, the voltage is 12 volts between A and B. And I'll give you C1, C2, C3, C4, and C5. Maybe. And I'll say, okay, what's the equivalent capacitance of this? Well, what do you see right away that you can reduce down?
All of them parallel.
Yeah, these two are in parallel. So I would go, all right, I can combine these just by doing what? By adding them. Now, here's what I would do. I would say, okay, well, now we've got C1, C2, and then I'll go down here and say, oh, this is C3, comma 4. C1, C2, C3, comma 4. Just to remind myself that that's the combination of 2 capacitors. And then here's C5. And then what am I going to do to these to get the equivalent capacitance? Yeah, exactly. They're in series. So you do the reciprocal thing. And that's pretty easy. So then once you have all of that, then you can back out. Well, once I have the equivalent capacitance, now I can figure out how much charge is stored on that capacitor, right? And if I know how much charge charge is stored on the whole equivalent capacitor. Well, these are in series, so what's true about the charge on capacitors in series? They're all the same. It's the same. So if I figure out, the charge on here is 5 microcoulombs, well, then it's, for the whole thing, then it's 5 microcoulombs for this, 5 microcoulombs for this, 5 microcoulombs for this, and 5 microcoulombs for this. Well, now I know the charge, and I know the capacitance. So guess what? If I know the charge and the capacitance, I can figure out the voltage. So now I know the voltage drop for this. I can figure out the voltage drop for this. I can figure out the voltage drop for this. Figure out the voltage drop for this. And it better all add up to the total voltage drop between A and B. Then once I know the voltage drops, I can back out and go back to these guys. Oh, I know the voltage drop between C3, 4. Figured that out. Well, now I know the voltage drop from here, and the voltage drop is the same as the voltage drop there. And now I can figure out how much charge is on those individually. If you know how to use those simple ideas, you can break these complicated things down. And this is very similar to the one that's on the test. So practice something like, there are some scary ones in the homework. The ones on the test are a little bit more simplified.
No diamonds.
Yeah, no diamonds on the test. But diamonds, you can just square the diamond. Just square the diamond. You make it all squared. Because wires are, you can do anything with wires on a circuit diagram if you want. All right. Now, so if you, question? Oh, I was just, the question was, what are we looking for in this problem? And I said, well, what if I give you the voltage, and I give you the capacitances, capacitize. How much charge is on each capacitor? What's the voltage drop across each capacitor? In other words, you're just solving the circuit. Everything you can figure out about them. And now, of course, you can figure out the energy on each capacitor. Because what is the energy on a capacitor? Well, and go back and look at that, because we didn't watch it in class. But the energy in a capacitor, well, you might think, it's just the charge on the capacitor times delta V. And if you said that, you would be wrong. But if you divide it by 2, you'd be okay. Why do you have to divide it by 2? Because, and we derived this, I'm not going to re-derive it right now, but if you have a capacitor, the first unit of charge that you put on it took no work to do at all. The last unit of charge you deposit on this capacitor took the most work. And it linearly gets harder as you add charge to the capacitor. And thus, what we're looking for is an average amount of work per charge that it took to put the charge on there. And so that's where you get the 1/2 from. Now, I'm not going to re-derive it. It's in your book. It's in one of the videos. But I'm going to say, here's how I always remember what the equation is for the energy stored on a capacitor. I go, well, look, I got a voltage here, right? A voltage drop across the capacitor, and I've got a certain amount of charge. I know that charge times voltage is joules, right? Coulombs times joules per coulomb is joules. And I just have to remember, cut it in half. Because the first unit was easy, the last unit was the hardest, so you take an average, divide by 2. Okay? Now, if you know that the energy stored in a capacitor is 1/2 Q delta V, 1/2, the charge, I'll put lowercase, it doesn't matter, lowercase, uppercase, it doesn't matter, times delta V. Delta V is the voltage drop across the capacitor. But what else do I know? I know that the capacitance is equal to the charge over delta V. So I can solve for charge. So charge is equal to C times delta V. So I'm going to substitute this in here. And when I do, I get 1/2. Well, C delta V times delta V is C delta V squared. So the energy stored in a capacitor is equal to 1/2 the capacitance times the voltage squared. Remember we did this with power? We had Ohm's law and we had I times V, and we did the same. It's the same kind of thing. Or the energy stored in a capacitor is 1/2. Well, I can solve this for delta V. Delta V is equal to Q over C. So if I substitute for delta V in there, I get Q over C times Q. That's Q squared over C. And these are the three equations that describe how much energy is in a capacitor depending on what you're given. And that's what really capacitors do for you in a circuit. They store energy up so that you can use it later when you want it. Finally, we have dielectrics. I think I briefly mentioned it. If you stuff a capacitor with gunk in there, now dielectric is another way of saying insulator. It's a material that does not conduct electricity easily. And what that material does, it does a lot for you. It keeps the plates apart so you don't accidentally touch the plates, because if you touch the plates, you'll discharge the capacitor, and your capacitor just becomes a very expensive wire. And because of the bound charges within the material and how it warps the electron shells around and so on, it allows you to put more charge on one of the plates and the other plate, negative, for the same voltage, which means you are increasing your capacitance. So it actually increases the capacitance of the capacitor. So that is, that's good. So I think we covered pretty much everything that I wanted to. Okay. And so anyway, I hope you haven't fallen asleep on your keyboard if you're watching this at home. That is all.